Hello everyone, this is part 3 of chapter 5, Turning Effects of Forces. In this video, we will be covering about the center of gravity of an object. So let's move on. We'll be covering only the first learning outcome in this video. The second learning outcome we'll cover in part 4 of this chapter. So in this video, we will learn about what exactly is center of gravity and how do we find the center of gravity of an object. So before we start, let's do a very quick recap of what we have covered in the previous 2 videos. Okay, which of the following is not an example of a turning effect of forces? The answer is B. Okay, because in A, you turn the knob of a door, the knob turns. In C, you use a spanner to tighten the knot, so the knot will turn. And then in D, you unscrew the lid of a container, the lid turns. So all these are examples whereby a force causes something to turn, except for B. Okay, B, you also exert a force, but the box doesn't turn. The box just moves along the floor, so there is no turning effect. Okay, for the second question, which of the following actions makes it easier to open a door? Okay, the answer is C. Okay, first thing you need to know when you are opening a door, the pivot, it will be at the hinge. So when you apply a force at the furthest point away from the hinge, you are increasing the perpendicular distance between the force and the pivot. So when you increase the perpendicular distance, it will have greater moments. And with a greater moments, it will be easier to open the door. Okay, so next, let's move on into center of gravity. So if I have a ruler, let's say it's a uniform meter ruler, and I ask you to balance it on your fingertip, where would you balance it at? Okay, I'm sure a lot of you will be able to tell me you will try to balance it at the 50 cm mark. So my question next is, why does a uniform meter ruler only balance at the 50 cm mark? Why can't I balance it at the 20 cm mark or the 80 cm mark? Okay, the reason is because the ruler has got a mass and has a weight. Okay, the ruler is not massless. So for example, in this case, this is my ruler, and this ruler has a weight. Okay, we always take it as the weight is at the center. And if I were to put my pivot exactly at where is the weight, you will see that, okay, you will see that there will be no moments caused by the weight. And therefore, I will have no turning effect, or this ruler will be balanced. So the moments is 0 because there's no perpendicular distance between the force and the pivot. Okay, and then next, if I were to shift my pivot or I were to balance at any other position like 20 cm mark or 80 cm mark, okay, so I put my pivot over here, you will see that my weight doesn't change. My weight is still at the center of the ruler. And this weight will actually create a clockwise moment. And this will cause the ruler to be unbalanced. This ruler will turn clockwise in this case. Okay, so center of gravity, you can read the rest yourself. We take it as the center of gravity. The definition for it is an imaginary point where the entire weight of the object seems to act. So center of gravity is actually a point. Okay, a point where the whole weight of the object appears to act as just a single point. Okay, so for regular objects with uniform density, we say that the center of gravity of the object is exactly at its center. Okay, it's exactly at center. So you can take a look over here. I have 3 different shapes. So these 3 different shapes are regular shapes. So I have a cylinder. The center of gravity will be exactly at the center. I have a cube. So the center of gravity will be exactly at the center. And over here, I have a ring. Okay, you cannot balance the ring at any other point except at the center. But just take note, the center of gravity can be outside of the object. Like in this case, the ring. Okay, the center of gravity is outside of the ring at the center over here. Okay, so how do I find the center of gravity for an irregular shape object? Okay, so over here I have a cardboard that's irregular in shape. It's very hard for me to determine where is the center of it and therefore determine where is the center of gravity. So I usually have to conduct an experiment to think about it. So first step, I need to make 3 different holes, okay, at different points on the cardboard. And then I am going to hang the cardboard onto this pin attached to a cord, okay? And I need to ensure that this cardboard can swing freely, okay? When this cardboard can swing freely, it will always come to a rest such that, so this is the front view, this is my pin, this cardboard will always come to a rest such that its center of gravity must always be directly below the pin, below the pivot. So the center of gravity is directly along this line. That is why, how do I get this line? I need to hang something called a plumb line. So a plumb line looks like this. It's just a string attached to a pendulum board. So I hang this plumb line in front of this cardboard or behind this cardboard so that I know where is the vertical distance or where is the straight line down. So I make a marking at the end where the plumb line mixed with the cardboard. And then after that, I'll just remove the entire cardboard and I'll just draw a single line. So the center of gravity must be along this line, vertical line down from the pivot. So I repeat the whole experiment on the 3 different holes. So this is the vertical line from point A, and this is the vertical line from point C, and this is the vertical line from point B. And I know the CG must be on the lines. So the CG must be on all 3 lines. So the CG must be at the intersection point of these 3 lines over here. Okay, so let's watch a video, okay, to show you how it works. Okay, there is no sound for this video.